Okay, this is the homework for chapter 3 for physics. Let's see. First question 60 says if an object's velocity time graph is a straight line parallel to the t-axis, so here's a velocity time graph, and we've got a straight line parallel to the t-axis. What can you conclude about the object's acceleration? We would say that it's 0. Keep in mind the slope of this graph is acceleration, so the slope is 0, which means acceleration is 0. Next question, what quantity is represented by the area underneath the velocity time graph? Well, if we have a velocity time graph of some sort, look at an easy one, and we're talking about area underneath, we have velocity in meters per second, time in seconds, and area is going to be like length times width, right? So you're going to multiply these units together if you're doing dimensional analysis. Seconds will cancel and you'll get meters. So we're talking about distance. Distance is in meters. Next question says a ball, after being hit, slows down and stops. Do the velocity and acceleration of the ball have the same signs? Well, no, the velocity vector is going to be moving in this direction, but the acceleration vector is going to be moving back in the opposite direction because it's actually decelerating or accelerating in the negative direction. If that's negative, then that's positive. Next question says if an object has 0 acceleration, does it mean its velocity is 0? So we can look at a graph then of velocity versus time, and we know the slope of this line would be 0. So this is an object that's traveling at, let's say, 3 meters per second, but it's not changing its velocity at all. So technically, if there's no change in velocity, then the acceleration is 0. Keep in mind that average acceleration is the change in velocity over change in time. So it's possible to have a change in velocity of nothing, like for example when we have constant motion, and that's 0 acceleration, but it doesn't have 0 velocity. So give an example. An example would be this: something moving at 3 meters per second. Okay, so here's this graph for 72. We want to figure out the interval in which the acceleration is the largest and the time interval during which the acceleration is the smallest. So he's got these dots here for us. So the acceleration is the greatest when the slope of this graph is the greatest. So that's obviously from 0 to 2.5 seconds here. And then the time interval where the acceleration is the smallest is the last. So that would be anything greater than, it looks like, this point here, which is, there's 12.5, so half of that. And I don't even know if they want us to use these dots, to be honest with you. So anything greater than 15 seconds, I mean, I'm not going to be picky about this answer because it's not real clear what interval they're talking about. You could say anything beyond 35 or 30. So just know that, acceleration is greatest here, and then it slows up over here. I won't be picky about whatever interval you choose. All right, we need to draw some velocity time graphs here for these ones. So here's velocity time. Okay, so for the first one, the velocity starts off slow and gains velocity at what seemingly is a constant rate. So we go like that. The velocity seems to be increasing. So the slope is increasing. So the slope is the velocity, so the velocity should be increasing, which it is. Next one, we've got a constant velocity here, and that's negative. So actually I should put the axis then down here, this in a different color as well. So the velocity starts off negative at a constant velocity, and then abruptly it changes to a positive constant velocity. So up here, jump and go like that. Negative constant velocity because we got a negative slope, and then it jumps positive and the slope goes up here. So the slope is the velocity. Here we've got a constant velocity that's positive, and then it jumps to a velocity that's lower. So it's got a slope that's positive, but then it's got a lower slope. So it just jumps to a lower velocity. Okay. Next question, let's talk about the moon. Gravity on the moon is about 1/6 the value of the Earth. So the question, would a bulb that's dropped on the moon be greater, equal, or lesser speed than a ball dropped at the same height on Earth? obviously it'd be less. If acceleration is less, then it's going to gain less velocity per increment of time. Okay, so it's going to take more time than for the ball to hit the ground because it's accelerating slower. Next question. Jupiter has about 3 times the gravitational acceleration. Suppose that a ball is thrown vertically upward with the same initial velocity on Earth and on Jupiter. Neglect the effects of Jupiter's air resistance and assume that gravity is the only force. How does the maximum height reached by the ball on Jupiter compare to the maximum height reached on Earth? Obviously, on Earth, it's going to go higher. Right? Same thing on the moon. If you were to throw us on the Earth and moon, the ball would go higher than the moon because if there's less acceleration, there's less of a force pulling it downward. All right, if the ball on Jupiter were thrown with an initial velocity that's 3 times greater, how would the effect of your answer be? All right, so the next question then is, if the ball on Jupiter were thrown with an initial velocity that is 3 times greater, how would this affect your answer to part A? So I'll do Earth first. On Earth, the distance final equals distance initial plus the initial velocity times time plus 1/2 the average acceleration times time squared. That's our equation for distance with average acceleration. On Jupiter then, and I'll actually subtract the distance initial over to the other side and just make this change in distance to simplify this a little bit. And so on Jupiter, it's the same thing, only this time the initial velocity is 3 times greater. And the acceleration is also 3 times greater, so I'm going to use 3a for A. On Jupiter, I'll just make this 3/2. All right, and then what I'm going to do is I'm going to factor out a 3 now. If I factor out a 3, then you can see, oops, that this quantity is the same as this quantity. So what that means is on Jupiter, we got 3 times this right here. So there's going to be 3 times the change in distance, right? Because this right here is the change in distance on Earth. So 3 times that will give us what we have on Jupiter. So we can use this math to do this analysis, which I think is obviously the only way to do it. All right, next question gives us a velocity time graph, and it says it wants us to find the acceleration of the moving object each of the times. So for part A, we want during the first 5 seconds of travel. So we're talking about this interval. We just need to find the slope for acceleration because that's the slope on a velocity time graph is the acceleration. So we'll do rise over run, which is rise is 30, run is 5. So that'd be about 6 meters per second squared, part A. Part B, between 5 and 10, that's obviously 0. Slope is 0. Between 10 and 15, we have a negative slope. So our rise is -10, and our run is 5, so it's -2 meters per second squared. Between 20 and 25, then, we have a rise of -20 and a run of 5, so it'd be -4 meters per second squared. All right, the next problem is we have a proton, we have initial velocity of 2.35 times 10 to the 5th meters per second. And it's accelerated at a constant acceleration of -1.1 times 10 to the 12th. And the time that we have that is 1.5 times 10 to the -7. We can use the definition of acceleration. It's change in velocity over change in time. The acceleration is -1.1 times 10 to the 12th. The time is 1.5 times 10 to the -7. And we know final minus initial velocity, where we have the initial velocity is 2.35 times 10 to the 5th. So we're just going to solve this for final velocity by multiplying both sides by 1.5 times 10 to the -7. And we can then add when we're done with this multiplication, and that gives us a final velocity of about 70,000 meters per second. Okay, next question. Marco's looking for a used sports car. He wants one with the greatest acceleration. Car A can go from 0 to 17.9. So we know acceleration is change in velocity over change in time. So car A has a change of velocity of 17.9 in 4 seconds. Car B has an acceleration of 22.4 in 3.5 seconds, and then car C, 26.8 in 6 seconds. And those calculate to 4.475, 6.4, and 4.46 repeating. So these are per second squared. So car B has the greatest acceleration. All right, I hope this helps.